Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we're going to discuss the mathematics behind radioactive decay, and we're going to work out a number of simple problems that allow you to be able to estimate certain features that constantly come up when you're dealing with radioactive nuclei. So to begin with, what I'd like to do is I'd like to define the half-life of a radioactive nucleus. And this idea is very simple and it's very intuitive. And I'd like to illustrate it with this diagram. So let's say we have the 131 isotope of iodine, and you can look up in the textbooks that decays by beta decay into the xenon isotope 131. And associated with this decay process is a quantity called the half-life, and that half-life is often abbreviated as tau 1/2 or T 1/2, right? And for this particular decay process, it turns out that half-life is about 8.04 days. Now, why do they call it a half-life? Well, it's very simple. If you have a collection of iodine 131 nuclei at T equals 0, let's say right now, right? And you come back 8.04 days later, what you will find is that on average, the number of nuclei that you had to begin with is just cut in half. And that just simply means that half the nuclei present have decayed into xenon over this time period of 8.04 days. So this is a probabilistic event. This is a probabilistic sequence of events. And you cannot ask the question, when will this particular atom decay, right? Or you cannot ask the question, if this one decays, when will this one decay? All you can do is say that after this half-life, half the number of nuclei that you originally started with have decayed, okay? So, again, you can't ask questions about a particular nucleus, but you can answer questions about aggregates. And the reason I like the half-life idea is because it's very simple, it's very intuitive, and it's very easy to remember. You don't forget it. We'll talk about another way of characterizing radioactive decay in the course of this lecture, and that other way of characterizing radioactive decay is derived from this very simple definition of a half-life. So you can ask the question, well, what are the half-lives of radioactive nuclei, right? What range do they span? Well, I'm not an expert, but I did some searching on the web, and what I found is I found that possibly the longest half-life known is this isotope of technetium. It has a half-life of something on the order of 10 to the 32 seconds. The shortest half-life I was able to find was for radon. That's something on the order of 7 nanoseconds. So you can see these half-lives span something like 40 orders of magnitude in time. There's a huge range. And each radioactive element has a different half-life associated with it. Nowadays, you can just go to the web and you can find the half-life for any particular isotope you care to think about. So these numbers are tabulated very nicely in very interactive tables that allow you to get at these numbers very quickly. And certainly in an exam situation, in this course, you'll be given the half-life, and then it's just up to you to know how to use it to solve a particular problem. So the law of radioactive decay that applies to alpha, beta, and gamma decay is the same. It just says that if you have a certain number of radioactive atoms, or a certain number of radioactive nuclei at T equal to 0, the number of radioactive nuclei that are there at a time T later can be calculated by multiplying n of t equal to 0 times 1/2 raised to the ratio of t over tau 1/2. So you can see how this works, right? When t is equal to tau 1/2, then this exponent is equal to 1, and the number of radioactive nuclei remaining is just cut by a factor of 1/2. If t is equal to 2 times the half-life, then this exponent has the value of 2. 1/2 raised to the 2 power is 1/4. And so after 2 half-lives, the number of radioactive particles remaining would be just 1/4 of what it was at the beginning. So that's the beauty of this definition. It's very intuitive, and it's very easy to remember. The half-life of these different radioisotopes, I have to say, is not affected by anything that we know of, right? So you can change the temperature, you can change the pressure, you can do what you want to a radioactive nucleus, but basically this this half-life, tau 1/2, is characteristic of the nucleus and not characteristic of the temperature or pressure or whatever that you exert on the particular nucleus. So just a graphical plot of how this works is shown in this slide, right? So here we have a nuclear reaction where radon decays by emission of an alpha particle. This particular nuclear reaction has a half-life of 3.8 days. And so, for instance, if we have, let's say, 20,000 radon nuclei at t equal to 0, and we come back 3.8 days later, we'll have 10,000 of those nuclei remaining, and we'll have 10,000 of the polonium nuclei present. If we come back 7.6 days later, which is 2 half-lives, the number of radons remaining is 5,000. We come back three half-lives, the 5,000 gets cut down to 2,500, so on and so forth. So with this simple equation, right? With this simple equation here, you tell me the time and you tell me the half-life, and I can then predict this red curve in this plot, right? I can then predict how many radioactive nuclei remain after any time interval that you care to specify. So to just work out an example, right? There'll be a number of examples in this lecture just to illustrate these ideas. So here we have an isotope of strontium, strontium 91. It turns out that has a half-life of 9.7 hours. If I give you a sample that contains 120 grams of this radioisotope right now, and I come back in, let's say, 22.1 hours, how many grams are left? How many grams of the strontium 91 isotope are left? So you have to use the simple formula that we've written down. In this case, the time is equal to 22.1 hours. The half-life is 9.7, so the ratio of 22.1 to 9.7 is about 2.28. You raise 1/2 to the 2.28 power, multiply it by the original 120 grams, and what you find out is that after 22.1 hours, you would have about 24.7, maybe 25 grams, roughly 25 grams of that particular isotope left, right? So, again, you can use this formula to make precise predictions. If the time involved is an integer multiple of the half-life, then the calculation is very simple, because then you're just focused on these solid red dots on this curve, right? These are integer multiples of time in terms of the half-life of the particular isotope that you're interested in. There's another quantity that's defined in the literature, in textbooks, and that's referred to as the activity of a source. So the activity is just telling you how many decays per second the source is experiencing. And the reason that's interesting is because if you have counters, that's what you measure experimentally, right? You measure how many decays per second that are occurring at a particular point in time. It's much more difficult to mass out a sample and determine how much radioactive isotope is remaining in terms of grams or in terms of radioactive nuclei. It's much easier to measure this activity, R. So the way this discussion goes is you start with the original formula for radioactive decay, and then you realize that another way to write 1/2 is to just realize that e raised to the minus 0.693 is precisely equal to 1/2. So that allows you to substitute e to the minus 0.693 in this square brackets for 1/2, and that then allows you to write the decay equation in terms of an exponential, right? So this allows you to go from 1/2 raised to a power. Now you're evaluating an exponential function. The price you have to pay is you have to introduce this additional factor of 0.693. So it's conventional to define a quantity called the decay constant, which is written as the symbol lambda, and lambda is defined as 0.693 over the half-life. And this decay constant has units of 1/2. So it's telling you how many decays per second this radioactive source is experiencing. And it allows you to rewrite this form of the decay law in terms of an exponential. N0 is the number of radioactive elements that you have at t equal to 0. Lambda is the decay constant that's related to the half-life by this equation. And so now you can calculate the number of particles, radioactive particles that remain by just evaluating an exponential function instead of raising 1/2 to some power. It's also useful to define the number of decays per second after a time t. So this is the activity that you would expect if you wait a time t. And that activity R of t is defined as the change in the number of radioactive particles with respect to time t. And just by taking a simple derivative of this equation, you can find that this activity R as a function of t is just equal to this decay constant lambda times n of t. We've got an expression for n of t, right? So we can plug that in, and we're then left with this new equation which says the rate of decay after a time t is equal to the rate of decay at time t equal to 0, right, times e to the minus lambda times t, right? So this quantity lambda times n0 is called the activity of the source. It's the decay rate of the source when t is equal to 0. And of course, it's always up to you to define what t equals 0 is. That depends on the particular experiment you're measuring. So for instance, you could have a radioactive source. You could put a counter next to it. And at this point in time, you could measure that there are 1,000 decays per second that are coming from that radioactive source. That would then allow you to define R0, right? R0 would be 1,000 decays per second right now. And then you could use this equation here to predict how many decays there would be if you came back, let's say, a day later, right? And so you put the detector at the same exact location with respect to the source, and you should then be able to predict how many decays per second you would get 24 hours later if you know the half-life of the particular particular radioactive nucleus that you're studying. So I think I just worked through some of those. I just worked through an example, right, to illustrate that point. So here in this example, we pretend we have a radioactive source that has a half-life of 30 minutes. So that means after 30 minutes, half of that radioactive material is decayed. And right now, right? At this point in time, at t equal to 0, we measure 80,000 decays per second are emanating from that source. So that's a measurement that we make. And then we want to know how many radioactive nuclei are present in that source at this particular point in time. Well, the number of radioactive nuclei that are present at this point in time, that's this quantity N0, right? And we know the half-life, right? That's given as 30 minutes, so we can calculate the lifetime. What we're interested in is calculating N0, and what we're measuring at this point in time is we're measuring R0 because we're measuring 80,000 decays per second. So 80,000 decays per second is equal to lambda times N0. What we just have to do is solve this equation for N0, and I work that out down here. You've got to do some conversion of units. You have to be careful about that. But the arithmetic is really simple, and what you find out is you got about 2 times 10 to the 8th radioactive nuclei present at this point in time to produce this decay rate of 80,000 per second. So you can actually estimate how many radioactive nuclei are in a sample just by measuring the decay rate very carefully, right? So that's another example of how you would use these equations. And there's only 3 or 4 equations that you need to know, right? They're pretty self-contained. So the arithmetic in this is pretty straightforward, I think. I like to well, this is an example of how you calculate the activity of a sample as a function of time. So here we have a sample of radon. Radon, this particular sample of radon has 4.75 times 10 to the 7th atoms of radon. Radon has a half-life of 3.8 days, 3.82 days. How many counts per second are you going to measure from this sample as a function of time? So what you're trying to calculate is you're trying to calculate the rate of decay as a function of time. You're given the half-life lambda, and you can estimate R0 because you're given the total number of atoms present in the source. So again, you've got to be careful with this conversion of time, right? In this case, you got to go from days back to seconds, and the arithmetic I just work out here, right? And so what you can do is you can check that tonight. But I think what you'll find that the rate of decay is going to be 99.7 decays per second times this e to the minus 2.1 times 10 to the minus 6 times t in seconds, right? So again, it's just an example of what you can do just given a simple problem. And the hope is that you can work through these problems with just by looking at a few of these examples. They're not overly difficult by any stretch of the imagination. So what I like to do is I like to end the lecture by talking about the radioactive dating idea. This is something that you tend to read in the newspaper once a month on a Sunday, right? And somebody's always using radioactive dating to estimate how old a particular artifact is. And I want to discuss this in terms of the carbon-12 and carbon-14 radioactive dating, and then we'll extend the discussion at the end to open it up to a more general case. So the interesting thing is that cosmic radiation that strikes the upper atmosphere has a way of turning the carbon-12 nucleus into a carbon-14 nucleus. And this carbon-14 nucleus decays, right? The half-life of carbon-14 is about 5,730 years. So once carbon-12 is converted to carbon-14, right, if you wait 5,730 years, there's a probability of 50% that one carbon-14 nucleus is decayed back to carbon-12. And based on the flux of cosmic rays striking the upper atmosphere, we now know that there's about one carbon-14 atom in about 7.4 times 10 to the 11th carbon-12 atoms, right? So there's very few carbon-14 atoms that are converted by this cosmic ray flux. But in the process of just living and eating, right, our bodies ingest this carbon-14, right? And so in principle, you know, for every 7.4 times 10 to the 11th carbon atoms in our body, there would be one carbon-14 nucleus. Now that carbon-14 nucleus decays in a particular way, and you can measure that decay rate. And in the process of measuring that decay rate, you can then infer how much carbon-14 is in a particular part of your body, right? So the argument is that the carbon-14 is uniformly distributed throughout your bones. And that carbon-14 ratio, the ratio of carbon-14 to carbon-12 remains constant over time. When you die, when you stop eating new food, then what happens is that carbon-14 starts to decay. And so if you give me an object, right, and and I measure how many carbon-14 decays per second emanate from that object, I can then infer how many carbon-14 atoms must be in that object. I know how many carbon-14 atoms should have been in that object when it was alive. And so by measuring the difference between those two numbers, I can estimate how long that object has been dead, right? So that's the basic premise, right? Libby got the Nobel Prize for this in 1960 because he showed this was a very viable way to date ancient bones, ancient objects that have been alive. So to try to illustrate that, I'll just work out an example that I cooked up, right? Let's say you're walking along the Wabash River outside of Purdue. You happen to find an old bone on the shore, right? And what you do is you take that bone to a laboratory and you ask the laboratory to analyze what the carbon-14 content in that bone is. So let's pretend that the laboratory makes a measurement and they say, to our best guess, there's 35% of the carbon-14 in that bone now compared to what it would have been if it were alive today. So 65% of the carbon-14 is decayed, 35% remain, and you can measure that experimentally. That's a measurable quantity. So the question is, from that simple data, you know, can you date how old that bone is? In other words, when did that bone stop converting carbon-12 to carbon-14? When did it stop ingesting air and food from the earth? And it ceased intake of carbon-14. So the answer is, yeah, you can do it, right? I mean, it's a simple calculation. I use the exponential form of the decay law, right? What I'm trying to find out is I want to solve this equation for time t, right? Knowing the fact that the number of carbon-14s today compared to the number of carbon-14s at the death of the bone is equal to 0.35 or 35%, right? So you can see it's very simple, right? You just take the ratio of n of t divided by n0. You have to take, that's 0.35. That's what you measure experimentally. So you have to take the natural log of that, and then you have to solve for the time t. And knowing the half-life of this decay rate from carbon-14 to carbon-12, that decay rate is about 5,730 years, right? So that's the half-life. Every 5,730 years, half of the carbon-14 decays to carbon-12. So it's all over, right, with this line of the equation. You just have to follow through the arithmetic And what you estimate that that bone is about 8,680 years old. So that's the argument that is used routinely to estimate the age of animal bones that are found throughout the world. The argument relies on the fact that the flux of cosmic rays striking the upper atmosphere of the Earth has remained constant over this time frame of 8,680 years in this case, right? So everything goes back to the to this calibration factor that there's one carbon-14 atom and about 7.4 times 10 to the 11th carbon-12 atoms. That number is based on today's measurements, and that number is based on the flux of cosmic rays striking the upper atmosphere. So if the flux of cosmic rays striking the upper atmosphere has varied wildly over time, right, then this dating process is going to be it'll give questionable numbers, right? But everything seems very consistent, right? When you date these artifacts and then you compare them to the historical dates, there seems to be a reasonably good agreement. So it's a very, very good system for working back in time, right? It's all based on radioactive decay. So this is carbon-14, right? Carbon-14 is useful for dating organic objects that require food to be ingested in order to grow. But there are half dozen other different radioactive isotopes that allow you to go back and date ocean sediments, rocks, lunar samples, groundwater, and so on and so forth. Each of these radioactive isotopes have different half-lives, and the half-life has to correspond roughly to the time that you're trying to date. So there's a lot of possibilities, and all the measurements require you to know the half-life, and they require you to measure the activity of a particular decay that's characteristic of each of these radioactive isotopes. So I just wanted to mention that as an example. You see this often in the news, and try to explain the basis behind that calculation. So hopefully you have a better understanding of how it works. So that's all I wanted to do this week, right? We've sort of breezed through nuclear physics, just trying to give you an overview of what I think is interesting and important for you to know. We're not trying to turn you into nuclear physicists, but a lot of these things you just need to know in order to function in the world today. Next week, I'm going to do a few lectures on nuclear reactions, and in particular, I want to talk about fission and fusion nuclear reactions, and I want to describe those and give you some feel for how that works. And then there'll be a lecture that wraps up the course for the entire semester. So come on back next week. It'll be a short week of lectures, and we'll focus first on nuclear reactions. So thank you much.